Hello and welcome to Webinar Wednesdays presented by the Concrete Preservation Alliance. My name is Chris Ball. I'm Vice President with Vector Corrosion Technologies, and I will be your moderator today. I'd like to welcome everybody to this seminar today. This is the 8th installment of our 12-part series on bridge preservation technologies. And today's presentation is evaluating as-built conditions using non-destructive testing. The Concrete Preservation Alliance is a coalition of companies committed to promoting the best practices in the field of bridge preservation and sustainability within the construction industry. The construction industry is a large user of resources and raw materials, and by keeping structures in place, by maintaining and rehabilitation, this is one of the most sustainable practices that we can do. Concrete Preservation Alliance hosts the WeSaveStructures.info educational website, and this is where you registered for today's seminar. The Concrete Preservation Alliance consists of Vector Corrosion Technologies, Vector Corrosion Services, Ndt Corporation, Vector Construction, and a range of like-minded organizations around the world that are there to promote corrosion and concrete preservation technologies. The WeSaveStructures.info website, which I mentioned earlier, you went to the events tab to register for today's seminar. You will also be able to register for future seminars at that site. We also have the presentation slides and recordings of previous bridge preservation seminars at the same page. And once this presentation is over, you can revisit that same page to download today's slides and view the video presentation. Also, just like to mention that the WeSaveStructures.info website, under resources, that we have an environmental calculator. If you'd like to check that out, basically it'll give you all sorts of statistics and information about how much resources are preserved and pollution is avoided by keeping structures in place. We invite you to check that out. So today's presentation is going to be presented by Bill Horn from Ndt Corporation. Bill Horn is the president. Ndt Corporation for over 20 years has been providing engineers and owners high-resolution, non-destructive, and geophysical testing services. Personally, Bill is a registered professional engineer and has a wide range of experience in the construction industry for over 25 years, and is also considered a national expert on scour critical bridge evaluations for Federal Highway Administration. Just a little bit of housekeeping here. If you have any questions, we will have some time at the end for Q&A, so I encourage you to visit the Q&A tab on your screen and submit those as we are proceeding, and then we'll moderate questions and answers at the end. So today, this is the topic that Bill is going to be discussing, and also discussing how to use Ndt methods to develop load ratings and to assess the piles and foundations. I think that's a picture of Bill there. Bill, what are you doing on that structure?
Great. Yes, it is myself, Chris. We're testing some piles. We've got our sonic, ultrasonic testing, and we're testing for the embedment length of piles. This happened to be a new pile that was driven, and the owner wanted to verify the embedment depth. So we've got a series of sensors ratcheted to the top of the pile, and I'm about to impact it with a hammer, and the energy waves will propagate down through the pile, kind of like a waveguide, and those energy waves will be reflected off the tip of the pile and come back up to the surface. We have the velocity of the energy wave. We have the time it took to go down and back. Very easy calculation to calculate the length of the pile. So it was a great lead in, and thank you everybody for joining us here today. Wanted to just start our presentation with a little bit of Ndt testing theory, and we're going to then get into some of the testing methods. There's ASTM procedures out there. Some of the applications for new concrete, salvageability of concrete. We're going to talk about through testing, which is a modification of our sonic ultrasonic testing. A few other infrastructure examples, so we'll focus mostly on bridges, and then as Chris said, we will have a little opportunity for questions at the end. But the real headline is how energy waves propagate through different material. And we are recording these energy waves. We are recording the velocity of these energy waves. These are in nanoseconds. They go very, very quickly. These energy waves get reflected and refracted off various anomalies. We also record the amplitude and can look at the data and interpret the frequency domain of this data set that we're collecting. So we're going to do a little deeper dive and try to educate everybody on what sonic, ultrasonic testing, as NDT defines it, really is. The velocity, there's different types of energy waves. There's a compressional wave, there's a shear wave. They travel at different speeds and have a different fingerprint or a different signature, if you will. But as we record these velocity measurements, it's very easy to calculate the moduli value. I'm talking about Young's modulus, the bulk modulus of a material, or Poisson's ratio. So that information, based on velocity of basically sound waves, can be equated into the in situ compressive strength for concrete. That's the velocity testing. As far as the impact echo or the resonant frequency, the reflection, we're looking at boundary conditions, the thickness of a deck, the depth of a pile. Maybe there's some delamination that's going on. And again, we get another component of the strength as well. But the faster that these energy waves go, the stronger the material is. So a solid piece of concrete versus concrete that's punky or micro cracked, those velocities are going to go quicker in solid concrete. If there's a crack in the depth of a deck, whether it's a full depth or partial depth crack, we're going to be interpreting how the energy waves propagate around that crack and how fast they go. Same principle can be applied for subsurface conditions. Some rocks are harder than other rocks, granite and basalts versus some of the sedimentary rocks. Glacial till is much harder than clay or sand. So the same reflection and refraction will be applied to the subsurface layering as well. Here's a picture of our sonic ultrasonic testing equipment. On the left is a 4-sensor array. Each one of those black extensions have a sensor and a little spring that are in contact with the concrete wall. This is an abutment wall. On the right is the energy source. It's an air gun, fires a small specially designed steel bearing. It's hooked up to a tank of compressed nitrogen. Every time we pull the trigger, we get the same energy, the same mass, the same pressure, same energy is introduced. And those black sensors are spaced at specific distances apart. The first two, channel 1, channel 2, are about 6 inches apart, exactly 6 inches apart. Channel 2 and 3 are 12 inches apart, 3 and 4, again, 12 inches apart. So every time we pull the trigger over that 30-inch distance with this 4-sensor array, we get that information across that line, and then we move it and collect information in other areas. So if we look at a close-up of how these energy waves propagate, one travels along the surface, and that's where we're in contact with the energy, and we know the distance from the energy source. There's another energy wave that reflects and bounces back and forth. It kind of oscillates between the thickness of the concrete member, maybe a concrete deck in this case, and that energy is trapped, oscillating back and forth. We record the amplitude and then look at the frequency as part of the data analysis. A good example of what the real-time data that we see in the field is this screenshot here. The compressional wave is the first arriving wave. The shear wave has a signature. It's got a little double hitch where that comes in. And then the larger Raleigh wave with a much larger amplitude comes in and it bounces back and forth. So while this may look like a lot of squiggly lines, there's an awful lot of data and that can be interpreted from this. And this is the result of one sensor. We have 4 sensors on the 4-sensor array that I showed you before. Rendition of that 4-sensor array is here, and we talked about the velocity measurements. ASTM has a procedure to record pulse velocity measurements, and we follow that. So as you're dropping a pebble into a pond of water and you see the rings echo out on the surface, there's a third dimension where that ring or that pressure wave goes down to the bottom of the pond and then is reflected back up. That is a combination of what we're looking at here. So the velocity is the surface measurements, the rings on the surface. The impact echo I'll talk about shortly is going down and back. And if there's micro cracking in the concrete, that's going to slow these energy waves down. It's basically the speed of sound, and the speed of sound in competent concrete is 12 to 13,000 feet per second. The speed of sound in air is about 800 feet per second, a lot slower. But from this velocity information, we can correlate the in situ compressive strength of concrete from these sound waves. And every time we pull the trigger, we move that 4-sensor array into another transect or another area. We're getting compressive strength over that sensor array area. It's correlated with cores very often. And we're within 500 PSI of a core that might be extracted in a preliminary phase of investigation, taken out of its element to a lab, broken, and under the ASTM compression standards, and we would compare very, very well to those results. So just 2 examples here. The top 2, channel 22 and 21, are good, strong concrete, competent concrete. We have the signature that we would expect, the shear wave, compressional wave, Raleigh waves. The bottom 2, channel 20 and channel 19, those amplitudes start to get stretched out. And that's indicative of what we would consider to be less competent concrete, from some cracking, from some deterioration. Maybe some moisture is getting in there. So this is the real-time data that we see in the field. Now, the first rendition was the pulse velocity information. There's a second ASTM procedure that documents how to record impact echo or pulse impact echo measurements. And we record the velocity and the impact echo measurements simultaneously. This is the energy that gets trapped within the deck and oscillates between the boundary conditions, the red line going up and down, up and down. Now, let's say that deck might be 10 inches thick, but there's a delaminated section of the deck over on the right. There is a change in the boundary condition, and that depth of energy wave propagation is going to change because there's an air void, some moisture, the delamination in there. So we're recording information on impact echo and pulse velocity simultaneously. I said before that cracks can be evaluated. Now we're separating the energy sources and the sensors away from each other. This is multiple representation of multiple shots of data to determine, is this crack partial depth cracking or full depth crack? And just as a reference to it, again, the 4-sensor array has been separated to many, many receiving locations. The source is along one line. There's multiple sources, but by doing this and calculating the refraction of the energy wave, we can determine if the crack goes through the member completely. I'll talk a little bit later in the presentation about pile testing, but here's the impact echo. That's what we started with the slide that I was on. The energy wave goes down and comes back. We've got the velocity, we've got the time. It's very easy to calculate the length of embedded piles. So we've done a little bit of testing theory. Hopefully everybody can follow along with that. And we're going to get into some of the testing methodology now. The sonic ultrasonic, we've just gone and done a deeper dive on that, the 2 ASTM procedures. Ground penetrating radar is very valuable, and that's electromagnetic energy. We're going to talk a little bit about that. Very valuable tool. And a third one I put in here for today is seismic refraction survey. That's a larger energy source, and it's used to characterize subsurface conditions, general soil layering. The oil and gas and the mining industry has used this for years. But we're going to start with ground penetrating radar, referred to as GPR. It's electromagnetic energy. The antenna, the transducer and receiver is all in one shielded unit. The thing to remember is there are different frequencies. A low frequency antenna, 200 megahertz, for instance, or 400 megahertz, that's going to help define where some of the buried utilities might be. Taking the call before you dig location services to the next level. Maybe there's some underground tanks that could be evaluated or need to be located. Maybe there's a pile cap that needs to be defined on what the depth or the perimeter is. So that's the low frequency. The other end of the spectrum is the high frequency. This is used to evaluate concrete, 1500 megahertz, 2000 megahertz, even 2500 megahertz is good for locating rebar in concrete, confirming some of the deterioration in concrete. A mid-range frequency, if you put the low, mid, and high frequency, you can look through various thicknesses of concrete. The electromagnetic energy is reflected off conductive material. Metal is conductive, salt water is conductive, and we're really looking at the relative density of the material that we're testing. So here we have a mini, a 1500 megahertz antenna, handheld units about the size of an iron, scanning an abutment wall and locating the rebar. There's a wheel on it to track the distance. It records the signals in there, and then the data is downloaded for post-processing. The orange unit is a little bit larger on a 900 megahertz antenna. This was for, it's a nice mid-range frequency that will tell you the thickness of asphalt. This happens to be an arch bridge. So we have asphalt thickness, there's a deck below the asphalt, and as the arch trails away, there's a layer of soil between the slab and the grade and the barrel of the arch. So we would look at the roadway surface down, and very often we would go below the arch and look up because there's another concrete layer of the arch itself. So the 900 is kind of the middle frequency range. Now that orange unit gets even bigger with a 400 megahertz antenna. And as I said before, that's very popular for taking utility locations. More than just a paint on the sidewalk, we can go on private property, we can give you the depth of the utilities, low frequency utility location. Now, each one of these little parabolas or mountain spikes is an individual rebar, and there is the concrete cover on top of that. And over on the right, that signal gets washed out a little bit. It's kind of attenuated. It's fuzzy. There might be some moisture in there, maybe some beginning of delamination or deterioration of concrete. So when we see the clear parabolic spikes, we know that the rebar, where it is, and that the concrete is in good tech. If it gets a little fuzzy or washed out, that's where the signal indicates some deterioration. So the 900 megahertz on the left isn't necessarily looking at the condition of the concrete wall itself. It's looking behind the wall. Is there drainage issues? Is there weep holes? Is there voids or a groundwater table behind that? Whereas the mini, the handheld mini, we're up on a roof here, possibly going to be drilling some anchors, want to locate the rebar and obviously not hit the reinforcing. The low frequency antenna, we're going to go across the utilities so that these utilities run perpendicular to the curb line, we're going to run parallel with the curb line to cross over it. And that's an example of that. So just a quick review. It's great. A lot of engineering applications are out there. High frequency is going to locate the rebar or pre-stressing strands or PT tendons, and I'm going to talk briefly about that at the end. Delamination of rebar in concrete. A mid-range frequency might not tell you about the concrete slab, but it might tell you what's going on beneath the concrete slab, maybe a spillway in a hydroelectric facility or a floor slab in a manufacturing facility. The low frequencies are good for site investigations, utility locations, but please remember there are different frequency with GPR. That's the headline. So the other test I wanted to talk about here this afternoon is the Seismic Refraction Survey. There's an ASTM standard for that. This is a larger energy source. This is not an air gun. This is a shotgun shell, black powder shotgun shell, or sometimes we use a sledgehammer on a steel plate, but mostly a size gun. And our geophones are spaced out at 5 or 10 feet apart over a 100-foot line of geophones, maybe a 200-foot line, even 400 feet long. We have the energy source at the 0 station. We would then do it at the other end of the geophone line, maybe station 200 if it's a 200-foot line. We'd also do a energy source in the middle of that, and then we put those all together. We're done with that line. We pick up this wire with all the geophones. A geophone is just a magnet on a spring, and move that. So we could go every 50 feet, go every 100 feet, and collect data. General soil profiling data, but more specifically, usually we're interested in where is the bedrock. And we could do some north-south lines, some east-west lines, and actually come up with a contour map of the bedrock. Very strategically beneficial if that can be done before a subsurface exploration program. That way the borings can be strategically located to verify this. We were asked to do this on a bridge design and the preliminary design for a large bridge up in northern Maine. Shear wave velocity, there it is. That is a way to define the strength of rock. Caterpillar to this day uses shear wave velocity to determine rock rippability. RQD is another one, compressive strength's another one. Shear wave is a way to define the strength of rock. So we have the continuous data. It was the diagonal was the proposed alignment for the new bridge. We did a continuous seismic refraction survey along that hypotenuse, and then a series of lines that were parallel to the flow, the red ones there. And we did this in about 2 days. It was about 1,300 feet, a quarter of a mile or so across the river. 2 days worth of data gave a complete continuous contour of the rock in that area. They were preliminary geotechnical design. They could still determine, is it a shallow, deep foundation, even change some of the span lengths based on this preliminary information. So we're going to go into some testing applications, starting with concrete structures, the new and the reuse. For the concrete structures, don't underestimate the value of a good process for vibrating freshly poured concrete, making sure there's no consolidation issues and good bonding between the lifts. Or if there's an existing structure, it's used for salvageability determination and reuse, a good sustainable approach. As-built conditions, I've got some examples of precast box beams where there's some very surprising results. Slabs and walls and beams, hydro facilities, pipes, dams, what have you, a variety of applications out there. But if you take the forms down and saw this honeycombed void at the bottom of the pour on the abutment, everybody would have some concern. The engineer and the owner would want to know the extent of that void. Over on the right side, you can kind of see the presence of horizontal cold joints. Maybe they were waiting for the truck on a very hot summertime day. And by separating the energy source from the receivers or the sensors and taking multiple shots, we can target, is there a good bond over that horizontal cold joint? Pretty much where that line of 4 circles are, the one pink one. there was a horizontal cold joint there. So the question was, is it well bonded, or did the bottom concrete set up and the top concrete never have an opportunity to bond itself? Another example is up on a closure pour where we were asked, and there was some suspect of some anomalies in the middle of this pour. Again, the through testing by taking a lot of energy source readings and moving the sensors at a variety of different locations, we can generate a tomogram using tomography. And then once we have the full array of the tomogram set up through the software analysis, we can slice that 1 feet in, 3 feet in, 6 feet in, very similar to what the medical community does with ultrasounds on many of our organs. So, and there was an anomaly over on the lower left on the blue screen there, over about 3, down about 4. Was not a void because we still had velocities that equated to a strength of almost 4,000 psi, but it wasn't the 7,000 psi that the rest of that concrete was. So evaluating existing conditions and looking at an existing structure here, this happened to be a aqueduct, but could also be a bridge, would be built pretty much the same way. Evaluating the integrity of the concrete, knowing where the rebar is. Sometimes there's unknown conditions and there's no drawings available for what's the reinforcing, what's the concrete strength, possibly even collecting some laboratory analysis. Maybe you extract a core. There's a petrographic analysis that can tell us what the concrete is. Now, if we're looking back up on a roadway, on a bridge, the sonic system is on the left. That's modified now to a deck wheel that gets pushed across the bridge. And the radar is on that 3-wheeled component over on the right by the curb line. And we can complete a very typical bridge, 2 main spans and 2 approach spans in about a day. And we would do the one travel lane and a shoulder in the morning, the other in the afternoon, identifying where the good concrete is in green, the moderate concrete, maybe some of the bad, spalled, deteriorated concrete, probably near the headers, the expansion joints, near the scuppers, where the puddles are, is where you're going to see the weaker concrete, slower velocities. So very valuable in evaluating, should this be a partial depth deck replacement or should it be a full depth deck replacement? It's great to have these repair quantities ahead of time before the contractors for its bid and designed and bid, and the contractors on site with changes, because nobody likes changes. We do need access to whatever piece of material we are testing. Here we're doing some radar scanning in the top of a pier plinth, man lift. We've got certifications for all of the man lifts that are out there. Parking structures, there's a variety of cast in place concrete as well as precast members that are used on building these structures, and we evaluate them on a regular basis. Just a quick example of the sonic testing here in a beam or GPR over on a column, not necessarily a bridge, but a wide variety of infrastructure. I'll talk a little bit about some sheet pile. Often the abutments are held back by sheet pile or a retaining wall, and the sonic testing in the GPR is very valuable to determine, is there an anchor that is tied back to the shore to hold that sheet pile wall up? Once it's exposed, we can scan it and determine, is the rebar, what is the spacing of the rebar, what is the thickness or the geometry of that anchor? There's an example of 2 radar devices scanning that, and here's an example of our sonic system that's verifying the dimensions of the anchor, and more importantly, determining the strength of the concrete. So looking at how this might apply back to a bridge, again, access is a big part of the challenge. Here's a UB, as I refer to it, an underbridge inspection unit from the deck, very valuable in kind of a reverse articulating bucket truck to get down underneath. There was some box beams, precast voided box beams that we were asked to evaluate, verify the rebar, the pre-stressing, and determine that there was proper cover around the box beams and not voids or anything like that. Same box beam, a little different means of access. And our scanning is on the bottom, so we're verifying that the cover should be as designed and that the reinforcing and pre-stressing should be as designed. And in this case, everybody's hoping for 5.5 inches of cover on the bottom and continuous 5.5 inches between the bottom of the void and the bottom of the beam. I'm referencing that upper left-hand diagram. In reality, the green line is that 5.5 inch cover measurement. We didn't have 5.5 inches of cover. We had an erratic 2 to 3 inches of cover, in some cases left. The red line is the actual cover, and you're thinking, well, doesn't that mean there's a void up against the styrofoam void as designed? And isn't that where the reinforcing or where the pre-stressing strands lie? The answer is yes. And these pre-stressing strands in the rebar should be embedded. They're not. We would verify that by drilling in a small hole and using a borescope to verify the conditions, quantify the voids that should be filled, and make sure that, at least in this case, there is no corrosion yet on the strands themselves. But that should not be an air void. That should be fully embedded concrete. Quick example, just to look at the amplitude of the signal. There was putting a steel liner in a hydro facility just inside the concrete draft tube. So there's about a 1/2 inch annulus around the perimeter between the outside of the new steel liner and the inside of the old steel draft tube. That was to be grouted. There was anchor and anchor bolts, but there was also pressure grouting. And the question was, is there a good bond of the grout between the outside of the liner, steel liner, and the existing concrete draft tube? And the top example, top right, is our tight amplitude, just how we would want to see it. Well bonded, no voids, a highly attenuated signal. The debonded area that's maybe partially bonded would be the middle example. We still have some of those tighter amplitudes, but it's not the signature that we would want, and that dissipating attenuated signal is not what we would expect for competent concrete. The lower one, that amplitude stretches out even more, and that is no bonded. So there's a void there, and contractor needed to come in and top things off in a couple isolated locations. Good way to understand this for spillways, looking at the concrete, but also looking underneath the concrete, is a validation phase here. Is about a 30 by 30 foot area. It was cleaned and pressure washed, and we did ground penetrating radar in our sonic testing, quantified the integrity of the concrete. But also with the low frequency GPR, we looked below the concrete to determine, was it founded on a bedrock, was it founded on fill, or in some cases, was it founded in voids, and was there some sediment transport that was going on? Excuse me, all three conditions did exist at this one. So one radar antenna quantifies the concrete, another one looks below the concrete. Now I'm going to talk a little bit about through testing, which is where we separate the energy source from the receiver. We touched on that earlier on with the honeycombing and cold joint discussion, but the yellow arrows would be where the sensor in the gun would get information on this column base. Whereas the red arrows, now we've got the energy on one end of it and our single sensor on the other end of it. And we're testing through the base of this column. And then we would move 6 or 12 inches further in, do it again. So we're getting the through testing measurements for this particular piece of concrete. A couple other applications: grout under a pedestal or a column pedestal should be grouted, often high strength. Even bridge bearing pads have especially high strength grout. As long as there's a vertical edge, we could set our energy sources along the north side of this and all of our sensors along the west side of it. And we would get good information from all these crossing wave paths on 1/4 of this particular grout column pedestal. So very good application for that. But back to the bridge evaluation, classic reuse and salvageability of a structure. We did take some cores, but to verify the integrity of the concrete, the deck was coming off, the superstructure was not salvageable, But the substructures, there was a question, can they be salvaged? And the answer was, let's do some through testing on this deteriorated pier, prove to ourselves, the owner and the engineer, that the deterioration is only on the surface. So if the 6 or 8 or 10 inches of spalled concrete is chipped away, the core concrete is competent. So on the left, we've got our energy source, our gun shooting through, and on the right, we've got our sensors, and probably have a 1 foot by 1 foot grid pattern all along this. So a lot more data in the field, a lot more data in the office to analyze, but it proved that the core strength of these piers were well over 5,000 PSI. There was no reason to demolish that or put it in a landfill, and reuse of this pier was the conclusion. Concrete buttress, very similar. Again, we got to get on both sides of it. We can't do it from one side. So this required scaffolding on both sides, but we were able to generate that tomogram, the tomographic image again. And once we had all of the data into the software program, we could slice that buttress wherever we wanted. This was an outer ring, an outer slice, showing some of the weaker concrete, slower velocities, the oranges and the reds. You got in 18 inches, 2 feet, everything was blue and purple, 5,000 PSI, 6,000 PSI, salvageable. No reason to demo this, chip this concrete out. They can certainly salvage it. It's always cheaper to repair a structure than replace a structure. So I've got a couple more infrastructure examples. We're rounding the corner here and wanted to share them with some folks. Some are bridge related, some are not, but pipes, precast concrete cylindrical pipe that's used in municipal water supply and wastewater supply. We'll touch base in some pile testing, some marine structures, and then we'll close it out with just a few images of post-tension tendons. This is a precast concrete cylindrical pipe, PCCP. There's an inner concrete core, and then there's a metal membrane that has been blown out and bent. There is an outer core. Then that whole section is wrapped with pre-stressing strands, and then there's a kind of a mortar coating on the outside of that. This was a catastrophic failure. A lot of water was wasted. Flooded out a municipal area. It may have even launched boulders up in the air. So a very serious condition under these high pressure pipes. We do a lot of pipe testing, whether we're inside during an outage or a dewatering, or if the pipe needs to be operable, it just needs to be exposed. We do a lot of testing on the outside of pipes as well. We often attach our GPR or our sonic system to a pole. That allows us to get access to the top. A tunnel is just a big pipe to us, whether it's municipal transit tunnel or a water aquifer or tunnels associated with hydroelectric facilities. Testing the concrete here, the radar antenna is on the pole. So real quick, we're going to just look at this schematic again for the impact echo and how it reflects down on a pile. We have the velocity, we see the wave go right by, we know the velocity, we record the two-way travel time, and it bounces back up. And if there's anomalies, they can be defined as well. This works on concrete piles, timber piles, and steel piles. So that includes all of the deep foundations, even auger cast piles, end-bearing piles, H piles. Got a couple examples here. We need to have access to the pile. That's on the side of a drilled shaft over on the left, the top of a sheet pile, or the butt of a timber pile. And there's those ratchet straps on the right, hitting it with a hammer or with the air gun. A number of different energy sources. Here we're testing some sheet pile. We've got the 4-sensor array and the gun on the left. And here we've got the hammer and the ratchet straps on a marine dock, a floating dock, where we're testing. This happened to be a concrete filled pipe pile. And we were getting the dimensions, the embedment length here on these piles. Bridge load rating. This happened to be posted because there was deterioration in the flanges and the web of these 6 steel sheet H piles. So nobody knew how deep they were, and before they wanted to excavate down, so a splicing or a jacket repair option could be implemented. needed to know the bedrock. So the refraction survey pointed out the bedrock's about 22 feet down. We tested each of these piles very quickly, and the embedment length, you guessed it, about 22 feet deep. So these were end-bearing piles, very safe to excavate down in the gravel into the riverbed, a couple of 2-3 feet, do the repairs on the perforated steel in the splash zone, and the load posting was removed from this particular locally owned bridge. Timber piles here, it's always important for us to measure where the mud line is, and if there's borings and we have an understanding of what the geologic conditions are, that's valuable as well. So trying to understand that. The marine structures, certainly piles as they go into the marine sediment, then there's concrete beams to be evaluated, and a concrete deck could easily be a concrete bridge structure there. We're up on the concrete deck here testing it. Here we have the sensor using a rifle gun and sensors with a pole to save on our backs for working all day. Our sensors are waterproof, and in many cases we have to put them in the hands of divers. So if there is only access to the pile underwater, maybe there's a jacket in the splash zone, maybe there's a fender system that only allows access to the pile with a diver, we can operate. All of the equipment is very portable and can be done in a small little skiff. Here we've got the computer readout. We have audio communication with the diver, some hand signals to walk him through, make sure we're collecting repeatable data, and then move on to the next pile. So we're going to round things out here with just a brief example of post-tension tendons. I know there was another full presentation on PT tendons, but locating the voids, the anomalies, the air voids, the water voids, the grout that just never set up can be done with post-tension tendons using the sonic, ultrasonic, whether it's external tendons or internal tendons. It's really how that energy propagates around the tendon duct. If there's an air void, it's going to be quicker for the energy to stay in the internal concrete of that. If it's a solid grouted tendon, it will go right through it and we will get a different frequency. Here's an example of a segmental bridge with a lot of external tendons. And here is one of those tendons. We don't have the gun and we don't have the force sensor array. It's a little different energy source and a single channel sensor, but we're looking through the external duct. And right around 42 feet, there was an anomaly, wet sand that was in there. It was segregated. And it's the amplitude of that fifth example on the right that opened right up, and we can identify those anomalies right firsthand in the field. So internal tendons are, well, now we have to locate the internal tendons. Here there's some vertical tied tendons on the piers or internal tendons on the wings of these segmental sections. Got to pull out the ground penetrating radar. There's our handheld mini. We need to locate where the rebar is. We need to locate where the PT tendons are, such that when we go to test the internal tendons, we're directly over the tendon duct. And eventually we do need to open the tendon duct very carefully to verify the anomalies on the particular bridge. Each bridge, each tendon duct, each good or bad grout sample has its own little signature. So we have to do a couple of openings, and then we can recognize, have a baseline, if you will, to recognize the anomalies on other internal tendons. And we don't have to drill every single one, but we do have to have some ground truth measurements up front. Here we're up on the surface. We've identified where the internal tendons are on this segmental structure and are testing with the sonic, trying to verify where they are and if there are voids, water voids, air voids, grout that never set up. Then we have to do an opening. We carefully drill once we've marked it again, drill into it. We drill and measure with a magnet, drill and measure with a magnet. We're not going to damage any ducts. The sonic system works on metal ducts and plastic PVC ducts, both. So once we do the drilling, now we have a bore scope, and the intention there is to document the conditions, the corrosion that's going on within these tendons. And we don't want to get these bore scopes stuck, because this is not your Home Depot borescope. These are very sophisticated articulating heads. They do video images, they do still shots, and they can document the conditions, the as-built conditions. In the upper left, a big void. Those tendons should be, the wire strand should be filled, and in fact their corrosion is already starting on there. Some of the other voids that are just non-existent with some tendon corrosion. The lower right example is a vertical tendon duct, and that is standing water that's about 4 feet away from our drill entry point. And often we've drilled into tendons and have had 1, 2, 4, 5 gallons of water come pouring out, often bleed water that is left over from the grouting process. And knowing the extent of the voids is a very valuable piece of information when you get into the repair strategy and going forward with the quantities for the repair strategy and the condition of the tendons. So we've been doing, taking our system, pushing ourselves with evaluating PT tendons, evaluating pile lengths. Even back in the 90s when the big dig was going on in the Boston area, we were one of the first to be doing a lot of the pulse impact echo testing on pile testing when the PVC cross-hole logging PVC tubes were broken. The corrosion can be very bad, and once the corrosion starts on these strands, it can go very, very rapidly. So a good example of identifying where the concerns are and addressing them before there's a failed tendon or any sort of catastrophic failure. So NDT is very proud that we just don't sit idle. We're always looking for other innovative ideas. And here's 2 examples of deploying our ultrasonic testing equipment remotely, very innovatively. We've got an ROV, an underwater ROV on the left, and we've got a climbing robot on the right. So able to collect data on dams or in pipes or in outfalls, and not have to put divers or personnel or rope access people in harm's way. So that's one area we're focusing on. Another area is the microphone technology. There's some very exciting advancements with acoustics, and NDT is proud to be a leader in that area. This was to determine cracks in concrete rail ties with microphone technology. We didn't have time to stop and have a contact sensor on the tie. We're just rolling by with a slightly different energy source, but microphone technology that's bracketing both sides of the rails. That's where the loads are, and these cracks were covered by ballast, so they were not noticed, would have been missed, and not only can we feel the shear wave and compressional wave with a pre-amplified microphone, we can hear those energy waves as well. So I had kind of gotten through everything. I think the time is okay, Chris. Do we have any questions that we can touch base on?
Yes, yeah, for sure. And thank you for the excellent presentation, Bill. We do have quite a few questions, and the first question came in early. I think this was partially addressed. The question is, are these methods endorsed by codes and standards? And obviously you mentioned some ASTM standards in the presentation, so I would just suggest that they can download those at a later time or contact you directly for those. But what made me think about is, are there any other publications that you'd suggest that cover these types of techniques?
There are a lot, particularly PT tendons. There's a lot of great resources out there. ACI, RCRI has a lot of information, the PT Post-Tensioning Institute. So yes, often they are referencing existing ASTM standards, and we have a combination. We collect data from velocity data and impact echo data, and then we choose how to analyze it. And I think that's important enough to emphasize. It's the experience is very important when it comes to analyzing the data. And with over 25 years of experience, there's a lot of value that's offered in that.
Yeah, just to reiterate your point that you made earlier, is that that's two different types of data that are collected simultaneously in one pass. So
That's correct. And then we just evaluate, we pick and choose. Do we want to look at velocity information, or do we want to look at the amplitude and frequency information? And there's a lot of software that we have to make that very efficient and effective.
Yeah. Another interesting question. You mentioned the air gun, shooting the bearing at a consistent speed and mass. The question is, what if a hammer is used with variable impact duration? Does it influence the results effectively?
It really doesn't. Often the hammer is used for the pile length, and there's really only one high frequency signal when you hit the pile. That's kind of time zero, and we know what to record. All of these energy waves go so quickly. So it's either a pass fail, there it is, or there it's not. When it comes to concrete condition evaluation, that's where the velocity information is traveling out laterally. And we're trying to collect that over a large square footage, not just from one core location, but over a large square footage. And that's where we found the gun to be very repeatable with a high frequency energy source.
Excellent. Tarek asked, can the GPR determine the effective area of reinforcing in the concrete, or is it just to locate the rebars and qualitatively see if it's in good condition?
Good question. The GPR can verify first cover depth, very accurate for that. The lateral spacing of the reinforcing. What it cannot do is determine the bar diameter. And what we recommend is, if you need that, and often you do for a bridge load rating when you have no plans available and don't know what the reinforcing is if it's a number 4 bar or a number 8 bar, it makes a big difference. So by locating a shallow bar, a longitudinal and transverse bar, then it can be chipped out, drilled out a little bit, just the first 1 or 2 or 2.5 inches. Clearly expose the bar, measure it with a caliper, take a picture, and then we just patch it up. If somebody tells you that GPR can give you bar diameters, you heard it here today, that'd be a little suspect on that. Even if they say, oh, a packometer is great, that I can get a bar diameter from a packometer, they're not reliable. They're not repeatable for accurately determining bar diameter. I own packometers, and they're highly variable.
Okay. Just Brad had a similar question. I think you covered a fair amount of that, and just one section of his question is also how can you obtain the clearances with 2 layers of reinforcing? Many times I know you're shielded from one side by a layer of reinforcing. Maybe you can make a comment on that.
Yeah, that is a great point. If there's a lot of steel in the concrete member, we may not be able to get a reflected signal on the lower mat of steel. If it's 12 inches on center, 10 inches, 8 inches on center, there's probably enough non-reinforced concrete matrix for us to get a look at that bottom row. But if it's tight, big hydro facilities, heavily reinforced concrete members, often we may have an opportunity to get the top half from the top part of the member and then come in from the bottom. If it's a big slab, maybe it's a pedestal for a large motor, and if we can get on the underneath side. So there is some limitations if it's heavily reinforced. Most of your transportation structures that are 8 inches on center or 10 inches on center, we can get information on the top and the bottom row of steel. Does that answer that? Good question, though.
Yep. Yeah. Adrian asked, is it possible to determine the length of a steel sheet pile with a 4-point sensor?
Yes, it is. And we have other sensor arrays, 2 sensors, 3 sensors. We found that a 4-sensor array over about 30 inches, 6 inches, 12 inches apart is more optimal, easy to move around, and gets concrete strength in about 10 inches deep. But as far as the sheet pile, yes, we can get the length of any type of pile.
Yeah. Juan Jose asked, what happens with the testing if the surface of the concrete is wet or dry? Does that variable condition have any impact upon your testing or the results?
That's a good question, and I'll use the example of the 4-sensor array. The closest sensor to the energy source gives us information on the surface of the concrete, and then as we get further away from the energy source, we're getting information deeper into the concrete. So the 0 to 3 inch from sensor 1 might be wet, might be spalled, might be very punky, but if we go over 12 inches, go over 18 inches, now we're getting information maybe in the 3 to 6 depth range. And the furthest sensor would get us down into the maybe 9 or 10 inch range. But about 10 inches from the surface is the maximum that we can get concrete condition assessment with our typical 4-sensor array. Great questions this afternoon, Chris.
Yeah, no, it's been really good. And we'll take another couple, and then we'll have to cut it off just from a timing perspective. But Kimberly asks, you discussed the capability to assess pile embedment depth. What capabilities do you have to evaluate subsurface pile condition?
If we don't have access to it, we really only have how that reflected energy wave comes back. Now, in terms of sheet pile, they're very thin. You're going to get a depth. That's about all you get for the subsurface conditions. Now, in terms of a drilled shaft, 3-foot diameter, or a caisson, maybe the casing was pulled too quickly. If we have access all around the pile, and there's an anomaly, a void, groundwater has impacted the consolidation of the concrete, by testing around the perimeter of that large caisson, we can start to get a picture of the percentage of the cross-sectional area where that anomaly may exist. So if we go to the north side and we get a full depth reading, we know there's some competent concrete. If we come to the south side and we only go half that distance, then we can try to go on the east and west quadrants to identify the percentage area where that anomaly may extend across the cross-section. Did you follow that?
Yep, and we'll do one more quick one here. Is there a non-destructive method available that can locate concrete footing covered with several feet of soil?
Several feet of soil, it would be, I think we're in the mid-range or low-frequency GPR range. The answer is yes. Often we're asked to identify pile caps or footings if there's other installation or excavation. So 2 to 3 feet of granular soil, low frequency GPR. If there's ideal conditions, we've had depths with good information of 8, 9, even 10 feet. If there's clay or saltwater residue, sometimes our penetration might be limited to maybe 4 or 5 feet, but low frequency radar.
Okay, excellent. Well, we just have a few minutes left, and I definitely want to thank all of the people who submitted questions, and there were actually some we didn't get to, and some that maybe you didn't get a chance to ask. So we want to make sure that you have an opportunity to contact Bill directly. So right now you see his contact information. This will obviously be available on the slides when you can download them off the WeSaveStructures.info site. But feel free to reach Bill directly to answer any questions, either general questions or project-specific inquiries are welcome. Once again, we thank Bill for his time today. As I mentioned at the very beginning, this is our 8th in the series of 12 webinar Wednesdays. If you go back to the WeSaveStructures.info website on the events page, please go register for our upcoming seminars as well while it's fresh in your mind. The next seminar will be Matt Miltenberger from Vector Corrosion Services, which will cover impressed current cathodic protection for reinforced concrete. And in May, we will have David Whitmore from Vector Corrosion Technologies, who will be presenting on electrochemical treatments to extend the life of corroding substructures. And those electrochemical treatments would cover electrochemical chloride extraction and realkalization processes. And that brings us to the end of our seminar today, and it looks like we kept it to the time that we promised. Once again, thank you, Bill. Thank you for all of your participation, all of the questions, and please take a minute to go visit the WeSaveStructures.info website, and together let's go save some structures. Have a great rest of your day.
Thank you.